Hello everyone, my name is Anton Jackson, and today I'll be walking you through my final project on predicting human cognitive performance. During this project, we're going to look at how different lifestyle effects can influence cognition, and our main goal is to find the strongest predictors of cognitive performance so that we can take actionable steps to improve both cognitive and mental health outcomes. So the main questions we're going to try to answer are: can cognitive performance be predicted from lifestyle data, and which behaviors are most strongly associated with cognitive scores? Our project objectives are to use machine learning models to not only predict cognitive outcomes, but also extract some meaningful insights for improving mental performance in real world applications. Let's go and take a look at our dataset. The dataset that I chose is called Human Cognitive Performance Analysis, and it has 80,000 unique entries. The purpose of this dataset was to explore how different lifestyle factors affect cognitive performance. Some of the key variables include sleep, exercise, stress level, diet, screen time, and caffeine use. It also includes memory and reaction time tests, which are important cognitive benchmarks. I use the raw cognitive score, which is our target variable for regression modeling, and I created a new variable called cognitive level, which I'll go into later on, for classification into low, medium, and high performers. Now, before we begin our modeling process, we'll just take a quick look at our key variables first. So we'll start with age. This is the age of each individual represented as a numeric value between 18 and 59. Then we have gender. We have an even split with 48% male, 48% female, and then 4% is other. And then sleep duration, the average number of hours the individual sleeps in a night, so it ranges from 4 to 10 hours. And then we have clusters around the 6 and 8 hour mark. We have a self-reported metric, stress level, which is on a scale of 1 to 10, and 1 indicating no stress, 10 indicating extreme stress. Next, we have diet type, which is not very significant towards cognitive score, so we're not going to be going into that one too much. But we have daily screen time, and this is the average number of hours spent on digital screens, and it ranges from 1 to 12 hours. Next, we have exercise frequency, and we have 40% medium, 40% low, and then the other group at 20% is basically our high performers. Next, we have caffeine intake. So this is the amount of milligrams consumed in a day of caffeine, and it's on a scale of 0 to 499. And it seems like this one is capped at 499. Next, we have reaction time, and this is measured in milliseconds, and it ranges from 200 to 600. And then we have the memory test score on a scale of 40 to 99, and both of these show even distributions. Finally, we have cognitive score, which is our target variable, and it shows a bell-shaped curve. Next to that, we have AI predicted score, which we're going to omit from this test because we're already using a machine learning model. Before modeling, I cleaned and prepared the data in AI Studio first. So I used a few different operators. We'll start off with a nominal to binomial operator. And we use this to convert binary categorical variables. So for example, gender, male and female, this turns them into ones and zeros so that we can use them in our calculations. I also use the nominal to numerical operator to convert nominal variables, so things like diet type and exercise frequency. These variables have more than 2 possible values, for example, vegetarian, non-vegetarian, and vegan, so converting them to numerical form helps the model interpret the differences between each category. Next, we have normalize, so this operator basically accounts for differences in scale. So for example, caffeine intake, we have 499 as the max limit. But for other things like our converted variables, male and female, these have a scale of 0, 1, or 2. So this just accounts for those big differences so that it wouldn't affect our data. I also removed the relevant columns such as user ID and AI predicted score. And the data set was split into 70% training and then 30% testing. Next, we're going to use RapidMiner's auto model feature, and this will help us figure out which variables are most important for predicting cognitive scores. So we can see that reaction time and memory test score had strong correlations, and these were flagged as important. And this makes sense because both are directly tied to brain performance. On the other hand, categorical variables like diet type and gender showed little to no predictive power, so these were marked in red and had low correlation values. So we deselected these to focus on the more important variables instead. This step helped us clean our data and make sure we only use variables that mattered most for building our model. At the very bottom, you can see that the generalized linear model had the lowest relative error at 2.4%. So this is the model that we're going to go by for the rest of this project. So these are the results for our generalized linear model, which is a type of regression model. It had a relative error of just 2.4% with a correlation coefficient of 0.998, which is nearly perfect. The most important predictor was memory test score, followed by exercise frequency and sleep duration. And interestingly, age, caffeine intake, and stress had little to no weight in this model. So I'll walk you through some of our evaluation metrics for the generalized linear model. We'll start off with the root mean squared error at 1.579. And what this tells us is that on average, our predictions were only off by about 1 to 2 points from the actual cognitive score, which is a really good result since our cognitive score is on a scale of 0 to 100. Next, we have the absolute error at 0.949, and this is the average size of the errors regardless of direction, and it's also under 1 point, which shows high accuracy. Next, we have the relative error, which is 2.37%, and this means that our model predictions are on average within 2.37% of the true score. Our squared error is 2.499, and this is another way of measuring how far off our predictions are, and this is a very good value. It just means our model isn't making any big mistakes. And then finally, we have the correlation at 0.998, which is extremely close to 1. So this shows that our predicted scores and actual scores move almost perfectly together. So in other words, when the real cognitive score goes up, the predicted score goes up too at nearly the same rate. So together, these metrics show that the model is not only accurate, but also consistent and reliable. Now we'll take a look at the generalized linear model simulator. And what this does is it lets us adjust different input values and see how they impact the predicted cognitive score. So in this example, the model predicts a cognitive score of 58.239 based on the values that you see on the left, and each slider represents one of the input variables. And to the right, we see the important factors for this prediction. So the red bars represent features that negatively impact the score, and the green bars indicate features that positively support the score. And as you can see here, reaction time had the largest negative impact. So this means slower reaction times lower the predicted score, and a higher memory test score contributed positively to the prediction. Also, lower stress levels and more sleep also supported higher cognition, but to a much lesser extent. So what this simulator does is it gives us a visual breakdown of how the model is thinking, and it also helps to identify which lifestyle factors are most influential in determining cognitive performance. Now we'll go over some of the key findings from this model. There's some expected results, things such as frequent exercise, adequate sleep are consistent predictors of cognitive score. There's a few unexpected findings as well though. So we found that high and medium exercise frequencies have strong positive correlations. However, low exercise frequency has a significant negative correlation. And then small increases in screen time, especially when paired with high stress or low activity, have significant impacts on cognitive score. Also, higher daily caffeine intake led to lower cognitive scores, which isn't always expected since caffeine is seen by many as a mental performance booster in the short term. We also have stress level, which is the most significant negative predictor of cognitive score when not taking reaction time into account. And then overall, the only significant positive predictors were the duration of sleep and exercise frequency. Next, I wanted to explore not just the scores, but how individuals can be classified into different cognitive groups. And this allowed me to use classification models like logistic regression. So since cognitive score is such a broad spectrum, a logistic regression just helps us identify the more context-dependent effects of our variables. And to accomplish this, we just have to convert our target variable to a multinomial using the generate attributes operator. And what this does is it classifies cognitive score into 3 separate bins, low, medium, and high. So instead of a numerical scale, we'll just be predicting a new categorical variable, and we'll call this cognitive level. And once we've input the generate attributes operator, we can separate cognitive score into bins using a function, which I will show you right now. So you'll see our function in the upper left column. I use the generate attributes operator to bucket the cognitive scores into 3 different bins. So a low cognitive level will be classified as a cognitive score of less than 40. Medium would be a cognitive score between 41 and 70, and then high would be a cognitive score greater than 70. So we did this because we wanted to transform our regression problem into a classification problem, and this will just help us better understand what factors increase or decrease the likelihood of falling into each group. So it will simplify the interpretation of the model, and it makes the results more actionable for decision making. Here you'll see the performance of our logistic regression model. And it wasn't as accurate as our generalized linear model, but we still saw some strong results. So 92.7% accuracy and a 7.3% classification error is still really good. And here's a confusion matrix for our logistic regression model, and this will show us how well the model did at predicting cognitive performance levels. Starting in the upper left column, so these numbers along the diagonal show the correct predictions for low, medium, and high groups, and the rest of the numbers show where the model made mistakes. For example, some people who were actually low were classified as medium, and the same happened in reverse, but all of these mistakes were small compared to the true predictions. And then we also look at the class recall at the very bottom. So this will tell us how good the model was at finding each of the groups. And it did great across the board with the lowest recall still above 87%. To the far right, you'll see the class precision, and this will tell us how often the model was right when it predicted a group, and that was also high for all of the three classes with a perfect precision for the high group. Overall, this matrix tells us that our logistic regression model did a strong job across all categories. And here you can see our logistic regression coefficients table, which is comparing the low classification group to the rest of the groups. And the coefficient represents the strength and the direction of the relationship between the variable. So essentially for this table, we'll see that positive coefficients mean a higher chance of being classified as a low cognitive level. And the biggest contributors to a low classification are reaction time, stress level, daily screen time, caffeine intake, and low exercise frequency, which is going to be our baseline or comparison group. So that's why you see a 0 for coefficient and a question mark for the p-value. Here you'll see a simulation of a low cognitive performer similar to the simulation we did in the generalized linear model. And this will show us what a typical low cognitive performer might look like based on our model. And we can see that the model predicts this person has an 83% chance of being classified as a low cognitive group. The bar chart at the bottom highlights the top factors that drive that prediction. So the strongest factor is reaction time, which is to be expected. So slow responses heavily support a low classification. Other things like memory scores, more screen time, and lower sleep also increase the chances of being in this group. So if someone shows these traits, the model is highly confident they belong in the lower performing category. So we'll go over some of the key findings for the low cognitive performer. So caffeine intake contributes only slightly to being classified as a low performer, and memory and high exercise frequency reduce the chance of a low classification, but they're not strong enough to reverse it. And basically, the ideal low performer is someone with high screen time, high stress, low exercise, and slow reaction times. So these make a person most likely to be classified as low, even with good memory scores and sleep duration. Now let's take a look at the high classification versus all other groups. And for high performers, low reaction time and high memory scores were the most consistent predictors. And for this table, negative coefficients mean a higher chance of being classified as high cognitive level. So the biggest contributors were high exercise frequency, medium exercise frequency, memory test score, and sleep duration. And then we have the high cognitive performer simulation. So this profile is 83% likely to be a high cognitive level, and the key drivers are memory, high exercise frequency, and high sleep duration. So this simulation models a high-performing individual, and again, reaction time and memory are the biggest differentiators, while diet type still shows very minimal effects. And let's go over some of the key findings for both of our models. Across both the generalized linear model and logistic regression, the two most important variables were memory test score and reaction time. But since those could be classified as other measures of cognitive level, we took those out of the results. So the most important variables ended up being high exercise frequency and sleep duration. Also, screen time and caffeine intake only slightly reduce the likelihood of a high classification, but that can be outweighed by stronger protective behaviors. And individuals with strong memory, frequent exercise, long sleep duration, and fast reaction times are most likely to be classified as high, even with minor negative factors such as screen time and caffeine use. From comparing our two models, we actually got some pretty surprising results. First of all, caffeine intake and screen time increase odds of both low and high classifications. So what this could tell us is that high performers could have high caffeine and screen time, maybe due to being an overachiever with heavy tech use. And then we have the low performers who could just be underachievers with screen overuse. We also have stress levels, and stress levels appears to have a positive effect on high cognitive classification, and this could be due to a number of reasons. Stress may be associated with high pressure environments or performance driven routines, especially if paired with traits like high screen time and caffeine use. And there's also the matter of cortisol, which is a stress hormone that can increase cognitive performance in the short term. So that's a pretty interesting insight that I gained from this. Now let's just compare the results of our two models and how they differ from each other. Our generalized linear model was really good at making consistent and precise predictions, and it had the highest accuracy rate with the lowest rate of error. The logistic regression model, it was still a high accuracy, not nearly as much as the generalized linear model, but it was a lot more straightforward to interpret, and it gave us some usable insights that we can use to implement preventive strategies in the future. So based on both of our models, we have a few recommendations to improve cognitive performance. And these recommendations should focus on enhancing memory, reducing stress, promoting sleep, and encouraging regular exercise. Also, tools like memory games and mindfulness apps and sleep hygiene routines could all be tested in future studies separate from this one. So we'll start from the top. Promoting exercise, even moderate activity, can help individuals improve memory, reaction time, and overall mental clarity. Also, longer sleep durations are associated with significantly better cognitive outcomes. So improved sleep paired with high intensity exercise is probably one of the most effective things you can do to significantly boost overall cognition. Then we have high stress levels and high screen time, which are two variables that were consistently associated with lower cognitive scores. So taking a short break from screens, especially when working for long hours, may lead to higher quality work output and less time. Caffeine intake, this may improve cognitive scores if cognition is limited by tiredness or lack of sleep. However, higher intake was negatively associated with cognitive performance. So reducing overall caffeine dependency may help improve sustained levels of focus. And then lastly, we have reaction time and memory scores, and these were the two most predictive variables in both of our models. Although this may be from overlapping variables, it might be useful to implement training tools to improve reaction speed and memory retention. Future testing would need to be done to determine whether these variables have independent effects on cognition or if they are just additional measures of cognitive score. So what are some of my reflections and next steps? This project taught me a lot about working with real-world data. So things such as cleaning it, turning it into usable features, testing different models to make sense of it. But one of the biggest takeaways was looking for hidden insights in the data beyond the surface level insights that we gained. So, for example, we all know that long sleep durations and high frequency exercise can improve cognitive performance, but it was surprising to see things like stress and screen time show up in both the low and the high cognitive groups. So, I'd probably want to look for more interactions like those, such as like sleep or exercise. If I were to continue this project, I'd just like to test it on time-based data and add more detailed health inputs, possibly build a basic dashboard or tool to give users real-time feedback. I'd also like to explore the effects of reaction time and memory score and what kind of effect that has on the overall cognitive performance, because those could be seen as alternative ways to measure cognitive performance. So I want to know if that's actually interacting with our data negatively. I'd also like to use a decision tree or a random forest. Those aren't as accurate as what we did use, but I think they could still provide us with some good insights. And I'd like to track how different variables can change with age, so age-related interactions. For example, we all know that sleep is bad for our cognitive performance, but does it affect us more at 60 years old versus 18 years old? So things such as that, changes in impact over time. Overall, this project showed me how predictive modeling can be used to identify actionable lifestyle habits. Also in the future, I'd like to explore deep learning approaches and examine how personality or emotional state affects cognition. But further validation and exploration could strengthen those findings. Anyways, this was my presentation on improving cognitive performance, and I just want to thank you for watching. I hope you enjoyed this analysis and found the insights surprising and helpful, and maybe actionable in the future should you want to improve your own cognitive function. But I really enjoyed working on this project, and feel free to reach out with any questions. Thank you so much for your time.